Dear colleagues, students and YouTubers interested in demand response, thanks again for your attendance and thanks to cired 2017 committee for the acceptation of this poster. Our presentation will discuss several methodologies and proposals to evaluate and simplify demand response in ancillary services markets. This poster is a collaborative work between 5 Spanish universities that share out and develop their expertise in the research initiative called Reddit 2050. Specifically, this work is focused on a small customer segment, residential and commercial, because first, they explain an important amount of energy consumption. Second, this segment shows a growing consumption trend in the medium and long term. Third, a small segment also explains a high percent of system peak load, and traditionally, peak load defines the size and the planning of power systems. Fourth, demand response policies for a small segment remain unexplored because ISO think that it is easier and more reliable to manage a large customer than 100 of small customers. This might be true, but the reliability and flexibility of a small customer could be more interesting for power systems because loads are also distributed resources. And finally, the European Commission reported in 2015 that demand response has a considerable interest for the European economy. The Commission foresaw that demand-side response alone could save up to 100,000 million euros per year. Demand response participation in markets has to face up to important barriers: market regulation, a minimum level of flexible demand, ICT requirements, and cost. This barrier justifies the lack of participation of demand in a representative and open market. This slide shows the state of demand response affairs in markets. The participation of demand response does not match to its potential. So, it seems necessary the development of specific methods to evaluate and demonstrate. Due to the aforementioned reason, a main concern for Reddit 2050 research team is to evaluate and simulate the possibilities of demand response in ancillary services. Figure shows the pros and cons of demand response in these services. A problem is that fast models and tools are needed. Moreover, some barrier appears for the customer. For instance, the difficulty to understand the different names of services in each country. This figure shows the differences between the United States and European Union nomenclature. Additional and interesting incentives are market prices. Prices and megawatt requirement change for each ancillary service. For instance, in PJM, the framework market in this example. As it's shown in figure, synchronized and regulation services present different characteristics and price behavior. Problems such as price volatility or price forecasting are a concern for future Reddit 2050 developments. The second act of this video is the description of the methodologies we are going to use for evaluation purposes. The methodology for carrying out the work must exhibit some properties. First, the model should be universal. That to say, it is important to avoid any unnecessary complexity for aggregator and customers. That's to say, the same database of parameters. And to develop similar steps to build the whole model irrespective of the market of service. Second, demand response is a complex task, especially for a small segment. Therefore, several models and tools are needed to accomplish the task. For instance, we need to integrate model of basic technologies for demand response, whose interaction explains the behavior of response, ICT, appliances, and dwellings. Third, the robustness of the models. For example, other technical approaches for demand response developed a specific model for each market of service. In some cases, these models don't include relevant parameters, or they include those parameters through a change in equation without any physical sense. Demand response methods. The use of the same modeling basis for different demand response policies seems affordable with the use of physically based load modeling. This model represents the processes occurring between load and its service, involving physical information. This model usually has several components which use thermal electrical analogies. For example, the dwelling environment submodel, resistors that represent heat losses, in this case conduction or convection losses through wall or windows, as well as heat gains, solar radiation, or internal gains due to inhabitants or appliances, current sources. Also, the model takes into account heat storage from the specific heat of walls, indoor masses, or roof ground through capacitors. The appliance and its energy conversion into heat, space heating, cold, air conditioning, or hot water. This is represented by a current source that switches on and off, or it is modulated by the internal control mechanism. The internal control mechanism, for instance a thermostat, which draws the demand from the electrical grid. Models such as the one shown in the previous figure are third or higher order models. For example, Energy Plus software models. If the user considers in detail the heat losses, gains, or storage in each element, wall, roof, ground of the dwelling, or in the case the appliance has some kind of energy storage, a new capacitor. The higher the order of the system, the more complicated is its resolution and the aggregation of these models, and consequently the response is lagging with respect to ancillary services requirements. The boundary condition for model order reduction is to consider the effect of some thermal masses as a constant. This is due to the high inertia of these elements. This fact reduces the accuracy of the model, but allows a faster response. In each case, the user should balance the precision of the models against its response, selecting the best option according to the problem requirements. The participation in ancillary services requires a minimum level of load response, from 100 kW to several megawatts. To overcome this barrier while meeting the needs of system operators, efficient and easy aggregation methods have to be developed. In our case, the aggregation process joins loads with the same end use: air conditioning, water heater, thermal energy storage, in dwellings with similar characteristic, service, and location. The first alternative for the aggregation problem is to solve the state-space system for each load in a control group, and then obtain the power of the aggregated load through Monte Carlo simulation, and then the statistical distribution of a state variable. This procedure needs the simulation of a large amount of loads, 1,000 perhaps or 10,000, and this takes some time. The second alternative is taking the state, that's to say, the internal temperature X in each individual load into the control group as the realization of a stochastic process which follow the stochastic partial equation shown in the slide. This stochastic partial equation is driven by the state-space system of an average load whose parameters are the mean value of a state-space parameter in the control group. Of course, this is a simplification of the problem, and obviously the question is the average load representative enough for the overall control group? There are many different ICT alternatives available in the market that present different features. The most appropriate communication technology is influenced by the traffic characteristic and communication constraints of demand response. Figure shows a reference communication architecture where the main involved actors and communication networks are identified. OpenADR is assumed as application protocol because it is widely used for demand response worldwide. Independent system operator and aggregator are typically far away from each other. So, broadband technologies over long distances are required, such as optical fiber or long-term evolution. On the other side, the aggregators are typically close to their clients. In these cases, low-range technologies with lower data rates can be used, such as Zigbee or power line communication. In particular, narrowband PLC is being deployed in the last mile of AMI, mostly in European Union and China, but also in the United States or Australia. Another model and tools previously developed by Reddit 2050 are under study to be integrated in the medium term. For example, some of these concepts are price volatility and price forecasting. The possibility to develop algorithms for market prices is a topic of interest. Literature classifies prices and market risk according to its variance or standard deviation. But this usually is not true. The problem with price is to determine the randomness or deterministic behavior of a time series. And that is a very different question. More information about these tools and topics can be found in Reddit web pages. Third part of this video deals with the selection and integration of the most appropriate tools to solve a specific demand response problem. In our case, the evaluation on demand response capacities to provide ancillary services. The lifetime of the model. We mean to assess the dynamic response of the models according to ISO requirements. They range from seconds to some minutes after ISO requests the activation of specific resources, and also the time period during which model should provide feedback and data to the aggregator. PJM market rules and events have been analyzed since 2008. For instance, 98% of events in synchronized reserve last less than 40 minutes, and the average time is 11 minutes. But ISO for qualification of demand response might require longer periods, from 60 to 2 hours. For the simulation, authors have considered end uses with a high saturation and power. In this case, several heat pumps in a residential group of customers in the southeast of Spain in a winter period have been considered. The profile of these loads cover high price periods in ancillary services. The most suitable way to control demand is through the control of thermostat deadband. The scope. With respect to elemental models, different simulations have been performed with fourth, third, second, and first order models, with a time horizon around 60 minutes. First order model suits the dynamics of internal temperature with bounded errors which range 10–15%. Time response of models requires the use of stochastic partial differential equation to provide aggregator with a necessary time to manage control policies while responding to ISO requirements. The performance of OpenADR over narrowband PLC infrastructure is evaluated through simulation tools using as metric the latency under three different types of noise. Results show latency times which range from 6 to 12 seconds. The simulation work allowed modeling the round-trip latency based on statistical parameters such as the mean and standard deviation. Both are used to define the input vector B in the state space equations and the noise in a stochastic partial differential equation that we are going to solve in load models, but later. Mechanical latency, or the delay of appliance's compressor, is also considered through on-site testing. The reason is that this class of latency is of the same order of magnitude as ISO's delay requirements. That's to say, between minutes or a few seconds. The integrated model provides the aggregator two outputs: demand in kilowatts or in per unit, and the statistical distribution of state variables. That's to say, in our case, the internal temperature. The probability distribution function of internal temperature, X, also bring up the necessary information to feed the thermostat setpoint. Probability density functions are two, F1 and F0. The first is defined as the probability that a load is in on state on a temperature differential. F0 can be defined in a similar way, but for loads in the off state. Bottom figures show this function and their cumulative distribution functions. In the figure, each ball represents 10% of loads. Their location in F1 or F0 show us if appliances are switched on or off. Their location in horizontal axis show us the temperature of the dwelling. Let us explain the use of probability density function for demand response. If the power system test signal being received from ISO requests 25% reduction in load demand, the aggregator should determine the work of the thermostat that put offside the deadband at 25% of on load. That's to say, the area of function F1 should lose 25%. Afterwards, the test signal rises. The scenario changes to function F0. Again, the aggregator should determine the work of the thermostat that put offside the deadband 25% of load. That's to say, the area of function f0 should decrease. This area in gray color moves from if0 function to on function. Of course, some artificial neural network tool should help the aggregator to make possible and easier this task, to calibrate the so-called load regulator and the throttle and braking behavior of load. This slide shows an example of the response of the aggregated group. For the same market, for a test signal, ISO evaluates the performance score, taking into account the accuracy, the performance, and precision of load response. With this feedback and with artificial neural networks, the objective of Reddit 2050 in the medium term is to refine and tune the integrated tool while improving the scoring of performance of demand response in regulation and synchronous reserve markets. In conclusion, the integration of renewables arises interest for new flexible resources such as demand response. Reddit 2050 proposes insight, that's to say, integrated tools and methods to facilitate demand response participation, in this case in ancillary services. But new and specific tools are still needed. Their development is the Reddit objective for the next years. Authors would like to express their special thanks of gratitude to the Spanish government and European Commission, who gave us the opportunity to do this wonderful